Let me unpack why prime numbers of blades are used in rotating equipment for you. It is a fascinating bit of engineering that most people never think about. You see them everywhere. Turbines in power plants, jet engines, even the simple fan in your home. These spinning giants are marvels of design, but there is a hidden challenge: vibration. If not managed carefully, vibration can turn these powerful machines into destructive forces. It is a delicate dance between speed, material, and geometry. It starts with a fundamental concept in physics: vibration. Everything has a natural tendency to wiggle, even seemingly solid objects. Imagine a tuning fork. Strike it, and it vibrates at a specific pitch, its natural frequency. This is not just a quirk. It is a critical property of all materials and structures, dictating how they respond to external forces. Understanding this is our first step to unraveling the blade mystery. So, what exactly is a natural frequency? Think of it as the frequency at which an object will naturally oscillate if disturbed and then left to vibrate freely. Every bridge, building, and even your coffee mug has one, or usually many. These are not random. They are determined by the object's stiffness, mass, and shape. It is like a structure's unique musical note, a rhythm it prefers to dance to. Now, here is where things get interesting and potentially dangerous: resonance. If an external force repeatedly pushes an object at its natural frequency, the vibrations amplify. Instead of dying down, they build up, growing larger and larger. This phenomenon can be incredibly powerful, sometimes destructively so. It is the engineering equivalent of hitting the perfect note that makes a glass shatter. I will show you how resonance works using a simple analogy: pushing a child on a swing. If you push haphazardly, the swing just wiggles. But if you time your pushes perfectly, in sync with the swing's natural back and forth rhythm, it goes higher and higher with minimal effort. That perfect timing is the external force matching the swing's natural frequency. For a machine, that higher and higher can mean catastrophic failure. The key is understanding how this applies to rotating equipment. Consider a turbine rotor, for instance. It is not just spinning, it is a complex structure with many components, especially its blades. These blades are designed to interact with fluids, air, water, or steam to generate power or thrust. But their very presence and their rotation introduces forces that can lead to vibration. The spinning itself creates a dynamic environment. What is fascinating is how these forces manifest. As the rotor spins, each blade passes through different pressure zones or interacts with stationary components in its path. Think of a jet engine blade passing stationary guide vanes. Every time a blade whizzes past a fixed obstruction, it creates a momentary pressure fluctuation or a tiny tap. These taps happen repeatedly, creating a rhythmic excitation. The frequency of these taps is directly related to two things: the number of blades on the rotor and the speed at which the rotor is spinning. If you have, say, 5 blades, and the rotor completes 1 revolution per second, then 5 taps occur every second as each blade passes a given point. This gives us an excitation frequency. This is the external force that could potentially cause resonance. Now imagine the entire turbine assembly: the rotor, the casing, the bearings, the shaft. This whole system also has its own set of natural frequencies, often referred to as modes of vibration. These are not just single frequencies. Complex structures can vibrate in many different patterns or modes, each with its own specific natural frequency. Some modes might be the shaft bending, others the casing twisting. The danger emerges when the excitation frequency generated by the spinning blades aligns with one of the natural frequencies of the overall structure, or even the blades themselves. If these frequencies match, you get resonance. This can lead to rapid fatigue, cracks, structural damage, and ultimately, catastrophic failure. Engineers spend immense effort trying to avoid these resonance conditions. So, what are these modes that our original question touched upon? Think of a violin string. It can vibrate as a whole, its fundamental mode, or it can vibrate in 2 halves, 3 halves, and so on, creating different harmonics or overtones. Each of these distinct vibration patterns is a mode, and each mode has its own natural frequency. They are always discrete, integer-based patterns. This is crucial to addressing the decimal modes part of the question. You do not get a 2.5 mode of vibration in a physical structure. Modes are specific, distinct patterns, like the different ways a jump rope can be swung. You can have one big loop or two smaller loops, but not 2.5 loops simultaneously in a stable, resonant mode. They are fundamental properties, like steps on a ladder, not a continuous ramp. Now, let us tie this back to the number of blades. The number of blades directly dictates the primary frequency of the taps or excitations that the rotating component applies to the rest of the structure. If a rotor has n blades and spins at r revolutions per second, it will create an excitation force primarily at nr cycles per second hertz. This is your driving frequency, but it is not just nr. These taps are not perfectly smooth sine waves, they are more like impulses. Any impulsive or non-sinusoidal force also contains harmonics integer, multiples of its fundamental frequency. So, a system with n blades might also excite vibrations at 2nr, 3nr, and so on. These are higher-order excitation frequencies, and they also need to be considered. The core challenge for engineers is to design a system where the various excitation frequencies, the fundamental nr, and its harmonics do not overlap with any of the structure's natural frequencies or modes across the entire operating speed range. It is like trying to avoid hitting any of the landmines on a minefield while traversing it at various speeds. And here's the cool part. This is where prime numbers come into play. A prime number, by definition, is only divisible by 1 and itself. How does this help prevent resonance? It makes the set of excitation frequencies generated by the blades less likely to coincide with the natural frequencies of the surrounding structure or other components. Let us compare. Imagine you have a structure whose natural frequencies tend to be simple, multiples of certain base frequencies. For example, a component that vibrates easily at 2 times, 3 times, or 4 times the shaft rotational speed due to its symmetry. These are common structural modes that engineers often encounter. Building on that, we want to avoid matching these easily. Consider a rotor with an even number of blades, say 6. If this rotor spins at r RPM, it creates excitation at 6r, 12r, 18r, and so on. Notice a pattern? All these frequencies are multiples of 2 and 3. If the structure has a strong natural frequency at, say, 2r or 3r or 4r, due to some other factor, perhaps an uneven bearing support, then having 6 blades significantly increases the chance of a common multiple aligning and causing resonance. Now, let us look at a prime number of blades, like 7. The excitation frequencies will be 7r, 14r, 21r, etc. These frequencies are less likely to align with those simple 2r, 3r, or 4r natural modes of the structure. The multiples of 7 are distinct and do not share common factors with the lower, more common integer modes that frequently arise in structural design. The essence of it all is that prime numbers effectively scatter the excitation frequencies. They create a spectrum of driving forces whose harmonics are less likely to fall precisely on the typical, low-order natural frequencies of the surrounding static structure. It is like using a unique, complex rhythm that is harder for other instruments to accidentally play along with perfectly. It is about minimizing the chances of sympathetic vibration. Think of 2 tuning forks. If one is struck and a second one is identical, it will start to vibrate purely from the sound waves. By using a prime number of blades, engineers are essentially designing the first tuning fork to have a pitch that is very unlikely to match the favorite pitches of any nearby easily excited tuning forks. This principle is heavily applied in aircraft engine design, for example. The fan blades, compressor blades, and turbine blades are all carefully chosen to have specific prime numbers. This is not just about the rotating components themselves, but also about how they interact with the stationary stator vanes and the engine casing. Every component matters. Let us revisit the idea of modes dividing into decimals. This misconception likely comes from confusing the excitation frequency with the mode itself. The frequency of the driving force from the blades can be any value, and it can indeed be a decimal. But the natural modes of the structure are fixed, discrete patterns, each with its own specific, often interrelated natural frequency. Think of it this way. You can play any note on a piano excitation frequency, but the strings in the piano, the structure will only resonate strongly if your played note matches one of their natural frequencies. The strings do not develop decimal modes of vibration just because you play an off-key note. They either resonate or they do not, or they vibrate weakly. So, the choice of a prime number of blades is a probabilistic strategy. It does not guarantee the complete absence of resonance, but it significantly reduces the probability that the periodic forces generated by the blades will align with a natural frequency of a critical structural component. It is about designing for robustness and safety. Of course, blade count is not the only factor. Engineers also consider material properties, blade geometry, damping mechanisms, and even operating speed restrictions. Sometimes, a non-prime number of blades might be chosen for aerodynamic efficiency or manufacturing reasons, but then other design solutions, like adding dampers, must compensate for the increased risk of resonance. What emerges is a picture of incredibly complex engineering challenges. Modern turbines and jet engines operate at immense speeds and under extreme conditions. Every detail, down to the number of blades, is painstakingly analyzed and optimized to ensure both performance and safety. It is a testament to the meticulous work of engineers. So, the next time you see a jet engine or a wind turbine, you will know there is a subtle but powerful mathematical principle at work in its design. It is not just about making things spin fast. It is about making them spin safely and reliably for years, even decades. The simplicity of prime numbers plays a crucial role in managing the inherent complexities of vibration. To reiterate, modes of vibration are fixed, discrete patterns unique to a structure, each with its own distinct natural frequency. The division is not of the mode itself into decimals, but rather the engineer's careful manipulation of the forcing frequencies from the blades to avoid dividing neatly into the natural frequencies of the system, thus preventing resonance. The core idea is that engineers leverage the unique mathematical properties of prime numbers to create a mismatch between the frequencies at which a rotating component excites the system and the frequencies at which the system naturally wants to vibrate. This sophisticated strategy significantly reduces the risk of dangerous resonance, ensuring our incredible machines can operate safely and efficiently.